This conference will now be recorded.
Ashley, are you going to give an introduction or something like that, or do I just start talking? Or
I did do the introduction. This is Jeff Jowett at MEGGER. So if you would like to go
okay,
ahead and start the presentation, please.
okay.
Jeff, would you like to begin?
I'm ready when you are.
I'm ready. Do you see the presentation up on your screen, the PowerPoint?
No, I don't.
Okay, because it is on the slide right now for yourself.
All right, I see that. Yeah,
Okay,
yeah.
so
My bio's up there now,
yep, we'll go ahead and get started now.
and this is going to be an hour, right? I should have settled that. An hour.
Correct. Correct. As long
Okay,
as,
I'm ready.
yes, as
I'm
long as
ready.
the
Go ahead.
slide.
This conference will now be recorded.
Okay, Jeff, go ahead.
Good day, everyone, and welcome to our presentation on the fundamentals of ground testing. And I should indicate that to really exhaust this topic would take a full day of presentations easily. So this particular initial presentation is just going to cover the basic fundamentals, give you a general idea, and then certainly give you a lot of direction regarding whatever areas you might be concerned about, with. And you are welcome subsequently to contact me, and I will be glad to help you with any additional questions or additional areas of pursuit. Next. Okay, can we move the slide? Do you hearing me? Uh-oh. Actually, have we lost contact? Okay, so I pretty much said this is just a fundamental. This is just a fundamental presentation today. We'll go over the basics. We won't have time to go into a lot of in-depth on particular procedures, but we will certainly get you off dead center and get you started. Next. Okay, basically we're talking about grounding then, which is establishing a electrical contact between your system and the earth in general. And these are the principal issues that you're dealing with an adequate grounding system. Of course, everybody, depending on where you are, but people tend to think of lightning strikes first, because that's the most dramatic expression of where you need a good ground to clear a lightning strike out of your facility. And also fault currents, which I'm actually experiencing this right now because in Pennsylvania the power has gone out from a storm. And so you have all kind of issues like that where the utility has a problem on the line, and there are large fault currents can go through your electrical system, and you want to divert them into the ground and not into your electrical system. And then another one that's not thought about too much is static charges, especially in office environments where there's sensitive computer equipment, and in manufacturing environments where you have things like process control and so forth. Static can build up, and then that'll spark to wherever it can find a place to spark to. And so if that goes into your equipment, of course, that can cause serious problems. So you want to have a good grounding system in place to constantly bleed that off so that it doesn't build up to the point where it sparks. And then, of course, you have all kinds of external interferences from things like radio frequencies and noise off of the utility and so forth. So these are all things that a good grounding system deals with. And the idea of it is to have a low impedance path into the earth so that these problems and these currents are not circulating around in your electrical system, causing damage and causing a risk to personnel. Next. So this is pretty much what I just led into. The main thing is you don't want voltage gradients developing from equipment to ground, because something has opened up in the electrical system and you no longer have a path to ground, and now you can develop a voltage gradient, and a person touches the piece of equipment at the wrong time and is injured or killed. And you read this once in a while in the news from things like vending machines. That's an area where unfortunately that sometimes does occur. And then I mentioned lightning strikes, and the thing at the bottom there, which is not so dramatic, but very, very important and actually somewhat more pervasive, is that computer and communication equipment is very sensitive and runs on very small voltage gradients. And so a little bit of noise that doesn't affect your electric lights or doesn't affect the operation of electric motors and things like that, but on computer and communication, that same level of noise can be devastating. So again, a grounding system guards against these problems. Next. Just a quick mention of our company. MEGGER has been a pioneer in this type of instrumentation and this type of testing. It goes back over a century, and we were one of the pioneer companies to come on the market with a ground tester. Next. Okay, and this is just a quick little nostalgic look at the old days. The main point I want to make here is that the fundamental ways of doing a ground test are essentially the same now as they were when these photos were taken, and we'll talk about that before the end of the webinar. We'll cover that a little bit, but the main improvements that have come with equipment, you see that on the left, the operator there has a fairly large box, which is probably wooden. And the main improvements that have come about in testing equipment has to do with all sorts of things like accuracy, speed, ease of use, additional convenience functions that you can run, and so forth. So the fundamentals of ground testing, which we're going to discuss, are still there and still in place, but the instrumentation has constantly been upgraded to give you, the operator, more and more to work with and to make your job more effective and easier. Next. Okay, we'll start with a look at the theory of how earth testing is fundamentally performed. Next. And there are two basic types of measurements that you're going to be interested in here, and that is resistivity and resistance. And they're very close together, and they sometimes get confused, but it is important to know the difference and apply them correctly. Resistivity has nothing to do with an actual electrical facility. Resistivity is the electrical properties of the composition of the soil itself. And we will take a look into that. The main point to note here is that to do that, you must have a 4-terminal ground tester. Now, ground testers come typically in 3-terminal and 4-terminal. And a 3-terminal will do resistance, but it will not do resistivity. So if you are purchasing equipment and take a look at what you might be doing in the future, if you're going to design or install a new ground, then you're going to want to know what the resistivity of the local soil is. So you'll need a 4-terminal tester to do that. Now, resistance, on the other hand, pertains to a human installation that is placed in the ground there to ground the electrical system. So this would be a grounding electrode. And how do you test that? How do you know how good it is? That's a resistance test. Okay, next. So we'll start then. We'll look at a little more in depth with resistivity. Next. And the main considerations here of doing resistivity measurements, if you have some land at your disposal, you can look for the lowest resistivity, which would be the best place to place a ground. So resistivity typically is the electrical conductance of the soil, its ability to conduct current. So you want low resistivity for a good ground. And if you do have land at your disposal, like you wanted to put in a tower someplace and have lightning protection, the spot where the resistivity is the lowest would be the place to do your installation. And then you also use resistivity measurements in designing a grounding system, what your electrode's going to look like. You can take a resistivity measurement, and in the old days, they used to use things like nomographs and a lot of hand calculations. Nowadays, it's much easier. You can get software, typically from the companies that make grounding materials, and the software will just ask you what is the resistance value that you want your grounding system to meet, and what is the resistivity of your local soil. And you put that information in there, and the software will crunch it, and then it will tell you, okay, you need 10 10-foot rods or whatever, and it will design the system for you. And just to remember that resistivity, it's referred, the bottom consideration there on this slide, resistivity varies throughout the year. So in the literature, they refer to it as a constant. That's a mathematical term. It's not a practical term. In reality, it varies with the time of year and the local conditions and so forth, and it can vary quite a lot. And so you need to keep that in mind, and you need to test for it. Next. So here's your fundamental setup for resistivity. There are other ones that exist, but this is the Wenner method, which is by far the most common method for taking a resistivity measurement. So note that you need 4 terminals because you've got 4 probes in the ground. And so on the this is a Kelvin bridge. Basically, you see this basic scheme applied in a lot of other types of instrumentation as well. So here they've applied it to ground resistivity testing. You've got 2 terminals on the outside that inject a test current through the soil. And then that's what the tester is going to look for, that current, and it's going to use that to base its measurement. And then the 2 inside probes are potential probes, and they sense the voltage drop caused by the resistance of the soil in between those 2 probes. And then the tester knows the potential drop, and it knows the current, and it uses Ohm's law. And up on your tester, it's in your display, it's going to post a number, and then that number is plugged into that equation that you see towards the bottom there. So that's rho equals 2 pi AR. So R is the resistance reading that you got off of your tester, and the A is the spacing of the probes, and the measurement is made to a depth that's equivalent to the spacing of those two potential probes. So if they're 10 feet apart, then you're looking 10 feet down. And then 2 pi, of course, just mathematical terms, and you calculate out your resistivity. And remember, this is a volumetric number. So this is in relation to ohm centimeters, not just ohms. Literature typically does this in centimeters. For your own purposes, you can do it in inches or feet or whatever you want. But if you're dealing with outside parties, you probably are, the industry standard is ohm centimeters. And so you're probably going to work in that. Next. So this, okay, so again, I kind of pretty much covered these. These are the variables then, which I think I pretty much covered. Okay, next. And so then you calculate out your 2 pi AR. In the old days, you used to have to do that manually, but nowadays the real sophisticated testers will do that for you. So it reduces human error. It speeds up. You get your answer real quick. And it also helps to reduce this. If you're dealing with third parties, it's a whole different world. If you're testing for yourself, then it's not too bad. You know, you're kind of calling the shots. But if you have an inspector involved, or you have a client involved, or anybody like that, then as many variables as you can eliminate, that's to the good, because it reduces the amount of dialogue back and forth and, oh, I don't understand this, or why did you do that? So it's a good idea to everybody to kind of stay on the same base. Next. Okay, so that's a quick look at resistivity. So I think it kind of describes basically how you take the measurement and what you do with the data when you get that. And so now we'll move on and we'll take a look at resistance. So this is where your grounding electrode comes into play. So this is your ground rod you see sticking up outside of a building someplace. And so how good is that? Well, you know, those things will corrode away underground. They're basically copper-clad stainless steel is what they usually are. And they'll corrode away. And I've been to sites where you could grab a hold of that like you see in the picture and just pull it out, because there's not much left underground. So it's a good idea to test this. You have to test it upon installation to make sure that you met spec, but then you should test it periodically thereafter, because a lot of things can cause that to change. And what's that is there for is basically, keep in mind, that's there to divert currents into the ground that you don't want in your electrical system. If it's a lightning stroke, then the gradient on the earth evens up with the gradient in the clouds, and that's what becomes of it. If it's a utility fault, then it's got to go back where it came from, which would be the utility generator that services your site. Okay, next. So the main thing on this is a grounding electrode can be something like a single driven rod, which is what most people think of, and it can also be a complex system. So you can have a lot of an array of driven rods that are connected together, or you can have a grid or a mesh. The main thing to remember here is, from the standpoint of just about everything I'm going to talk about, and from the standpoint of testing and maintenance, they're all pretty much the same. It's just how much metal can you put into the ground to help get your fault currents into the ground and out of your electrical system. And the more metal you put in the ground, the lower the resistance is going to be, and the better your grounding electrode is going to operate. And so from the standpoint of testing it and maintaining it, they're all pretty much the same. Next. Okay, why do you want to have low resistance? Well, of course, one of the main things that people think about is you want to help out the the circuit breakers and the protective system so that they'll sense fault disturbances, current disturbances, and they'll trip on time. And you want to reduce potential rises. So basically, you don't want your equipment to become energized and become a source of shock. And then we mentioned at the bottom step and touch potentials, and I think we have a slide coming up on that. So let's go to the next one. Okay, yeah, good. And this is step and touch potentials. You see this, especially if you're dealing with substation testing. These are protective measures. So you might think, well, okay, I've been talking about all this current going into the ground, which is what this is basically all about. So how come people aren't getting electrocuted all the time just walking around? Well, the reason for that is because there's so much ground, it's everywhere. So the currents that get put into the ground, they even out over an enormous space. And so you're outside walking around, you're not getting a voltage gradient between your feet. But if you get close to a substation, then the danger starts to rise, because as the fault currents go back to the substation where they came from, then of course the concentration of current is going to rise. So the substation needs to be protected. Step potential would be across the human distance of a typical human step, so that you don't develop a voltage gradient between your feet and become shocked if you're walking past. And then step potential, of course, would be if you touch the fence. And so what you do is for a step potential, you just place two probes in the ground, and you've got your current going to your substation fence, and you've got your other current going to a probe somewhere out, a distant point out in the soil, so that you have a test current now going from the fence to the current probe that we see in the front of the picture here. And then you've got two other potential probes about 3 feet apart in the vicinity of the substation, and you're going to get a resistance measurement between, this distance of a human step, and then you plug that into an equation with the maximum fault current that a substation could see, and using Ohm's law, then you calculate out, and you don't want to have any more than 50 volts of step potential so that a human will not get shocked. Generally, a human won't be shocked at below 50 volts. And for touch potential, it's the same thing, except that you're going to have one of your potential probes up on the fence and the other one about 3 feet away on a probe driven into the ground. And you do the same thing and calculate out your touch potential, and you want that below 50 volts. Next. And this is just a simple slide to show you how fault gradients level off quickly with a good ground. All right, now we'll take a look at the components of the passage of fault current to ground and how a grounding electrode operates. Remember, whether it's a single rod like this or whether it's a whole big grid, the idea is that as fault current goes to ground through this device, through the ground rod or whatever, it's going to encounter resistance from the surrounding earth. But as it gets further and further away, initially, of course, the resistance is going to rise because there's going to be more and more earth for the current to travel through. But here's the critical point. If that continued to rise forever, there would be no point in grounding a system. It would be ineffective. But what happens is, as the current gets further away from the electrode, it has more and more earth to spread out in. So at some point, there is no additional resistance added. And that point is what you need to know in order to evaluate your system, your grounding system. So if it levels off at, let's say, 5 ohms, you've got a good ground, you don't have anything to worry about. if the resistance levels off at 250 ohms, your ground's not working, and you got to do something about it. So this is what you're measuring then. This is what you're looking for when you're measuring the resistance of your grounding electrode. Next. So we'll take a look at theory a little bit, 2-pole and 3-pole measurements, and so we'll take a look at those individually. Next. And the main thing we want to call to attention here is that, let's see, these are some typical values. That's obviously a fundamental question. What do I want my system to be grounded to? You know, what resistance should it be grounded to? Well, the thing you see in the literature all the time comes from the National Electric Code is 25 ohms, but that's very forgiving. The code is concerned with protection from electrocution and fire. The code doesn't address itself to deeper considerations like how well is your system going to operate. So for system operation, you want to have actually a much lower value than 25 ohms. That's a forgiving value. So industry standard for like industrial and commercial is typically around 5 ohms. And for more demanding situations, computer room grounds, substation grounds, hospital grounds, things like that, they typically want even lower resistance, 1.5 ohms, or even sometimes less than 1 ohm. Next. This is the 2-pole measurement. We put this in here because this is commonly encountered in the literature. It's sometimes referred to as a dead earth measurement. You can use it, and it's widely done. It's very easy, but it's a real cheap and dirty measurement. And so what you're doing here, this is basically like hooking up a DMM. You shunt your tester into a 2-pole position. In the old days, you had to put paper clips or shunts between your terminals. Now with the modern testers, it's typically a selector switch position, and the tester does it internally. But you select 2 poles, and now that reduces a 3 or a 4-terminal tester down to 2 poles, and you're just going to run 2 leads, one to the ground that you're trying to test, and the other one goes out to a convenient low resistance point of return, which is typically they use the water pipe system. And then you energize your tester, and it's going to measure a loop resistance of that whole thing through the earth to the return, and then back through the lead to your tester. And it's going to give you a series loop resistance. And what you're counting on here to use this for a resistance of your grounding electrode, what you're counting on is that the water pipe system doesn't contribute very much to the measurement. So most of what you're seeing is going to be the resistance of your grounding electrode. The problem with this is it's highly irregular, it's prone to error. You have to just accept the measurement. So it is mentioned and it is covered in the IEEE 81, which is your ground testing standard. And if you need something to refer to deal with third-party interventions, then IEEE 81 is what you go to. It does mention, but it does not endorse the dead earth measurement, where this is principally used. It's a drop-dead measurement in situations where you basically just don't have any room to work. This would be in Manhattan. You have to get some kind of a reading on your system to satisfy the insurance company or whomever. And so your last resort is to do a 2-pole measurement. But again, bear in mind, it's just a drop-dead technique, and it's far preferable to do other techniques which are more thorough and more reliable, which we are going to talk about as we move along. Next. Okay, so I think I kind of covered that, the limitations of the two-pole measurement. Okay, next, we're going to look at a typical three-pole measurement, and this is the fundamental way to do a ground resistance test. This will operate with a tester that is either 3 or 4 poles. You can do this either way. The tester is going to inject, I should say, a test current into the ground. So you're going to have a current terminal, and you're going to take as long a lead as you can and drive a probe into the ground at maybe 100 feet away, let's say. Just try to get as much distance as you can. And now what that's going to do, when you energize the tester, that's going to put a test current in the ground from the current probe to your ground electrode that you're measuring. And the tester is going to use that current to make its measurement. And this is an alternating square wave. You do not put a DC current into the ground. A DC current would be far too subject to interference from other problems and things that are going on in the soil. So instead, typical testers will give you a frequency of something like 128 hertz, because that's close to a power frequency, but it's not dead on a power frequency. And so the tester looks for 128 hertz and it ignores everything else. And that's how you get a clean measurement out of potentially noisy environment. Good high-end testers typically will now give you the ability to adjust your test frequency. 128 is just typical, but in many cases you'll have a tester that can adjust the frequency, and so you look for the quietest frequency to run your test. And so then the potential probe, which the operator typically manipulates, the potential probe is going to be established in the ground at critical distances, and measurements are going to be taken. And what you're measuring now is the potential drop to the potential probe caused by the resistance of the intervening earth. So now you're seeing on your display the resistance to wherever the operator placed that potential probe. Next. And so you have kind of a step-by-step measurement here. You're going to typically take a series of measurements and you're going to plot them. Okay, next. All right, and so this is a typical setup, and I think, the main thing that we want to emphasize here now is that you're going to have an electrical field around the ground that you're testing, and you're going to have a similar field around your current probe, because of course it's putting current into the ground, and you don't want them interfering with each other. So you want your potential probe in between, and you want to try to take a series of measurements. If you take one measurement, it might be fine, but you're accepting that on faith. You don't have any proof. So you want to try to take a series of measurements. Okay, next. And so this is what we're looking for. We're going to graph the resistance measurements with distance. Okay, next. And all right, yeah, if we can keep clicking these, I think this is going to show you, yeah, well, okay, good. Yeah, it's kind of showing you that you're going to be moving the potential probe and you're going to be taking a series of measurements, and then typically you will graph them against distance. And what you're going to end up looking for then is an area. This graphic doesn't show it real distinctly, but you're going to want to look for an area that stays relatively constant in the middle, and that is your reading. And if that's below 5 ohms, you got a good ground. If that's up at 200 ohms, you got a bad ground. And so basically that's your fundamental test. And that is what is called fall of potential. Okay, next. So typical probe spacing, okay, they kind of speak for themselves. I don't think I need to comment on that too much. Now, here's the problem. Here is the not the only problem, but this is the most fundamental problem that you're going to run into in ground testing. And this is where your two zones, electrical zones around the probe and your test ground are overlapping. And if this happens, then you're moving your potential probe and you're taking measurements, but they're going to just keep going up. They're not going to level off. And so in this case, if you graphed it and if you showed this to a client, for instance, they would say, well, where is the resistance measurement here? And you really can't say that. You wouldn't have that information available. And so in these situations, the best thing to do is to get more distance on your current probe. So try to run it further out and try to retest. But in a lot of situations where your area around your test ground is constricted by highways and rivers and other people's property and all sorts of things like that, you can't necessarily always do that. So when that happens, then there are other test methods, which we're not going to go into today, but they do exist, test methods that are designed for dealing with this type of problem so you can actually get a coherent and reliable measurement off of this. Next. So fall of potential is the best method. If you can do fall of potential and graph it, that's the best way to go. It's fully in conformance with IEEE 81. So if you have third-party involvement, that stops a lot of argument right there. And then the operator has complete control of the test. But the problems with it are that it is fairly labor-intensive. It does take a bit of time to do, and of course, you can run into a situation like we saw in the previous graph where you didn't have enough room to test and enough distance on your current probe. Next. Okay, so it's labor intensive. It does have space constraints. The last one about, I think we have this at the end of the presentation about disconnecting from your power system. Okay, next. Now, a quick mention of, okay, simplified fall of potential. Simplified fall of potential method. This is a way of doing essentially the same thing, but without as much time spent. So if you're dealing with time constraints, then the next thing to do is go to simplified fall of potential. Next. And so the advantage, it's an adaptation of fall of potential. So it has basically all the advantages of fall of potential. But the main disadvantage is that it's not quite as reliable because there are a couple of assumptions are built into it, but it's not a huge disadvantage. Next. So here is simplified fall of potential. Kind of in a nutshell, you're going to do a little arithmetic, and you see that off to the side of the slide there. Instead of graphing all the way from your test ground out to your current probe, you're going to just take 3 measurements. So it's a lot less walking back and forth and a lot less work and time. You're going to take a measurement at half the distance, and then you're going to move in 10%, and you're going to move out 10%. And you're going to take those 3 measurements, and on the left side of that slide, you see you plug them into a little mathematical crunch, which in the old days you used to have to do that manually. Now with newer software and newer testers, this is frequently built in, and so you just engage it, and the tester does the arithmetic for you. But basically, what it does is it calculates out the percentage error. And so let's suppose you were buying a multimeter, a DMM, and you looked at the accuracy statement and it said 10%. Well, you would say, this thing's a piece of junk, I can't use this, and you wouldn't buy it. So the same thing with this. If you get a rather large potential error, accuracy error, then your test result wasn't very reliable. What that kind of told you was you took those measurements on the rising part of what would be the graph instead of on a flat part. If you get a real nice calculation, let's say you're under 2%, well, in a DMM, that wouldn't be too bad. And so for a grounding measurement, same logic, that's not too bad. So your result was pretty accurate and you could accept that. So that's basically the pass-fail crunch that's built into doing a simplified fall of potential. Okay, next. Oh my goodness, are we at the end of the presentation already? Yikes, I thought there were more slides on here. My apologies. Okay, there are a couple of other things that I think we have some remaining time, about maybe another 15 minutes or so. So there are a couple of things that I can talk about in addition. Can we back up a bit? Okay, anyway, I can still talk about a few other considerations. One of the things that I wanted to kind of add on to the end, although I guess I didn't get the opportunity to do so, is the Clampon. And that's the only change, fundamental change from fundamental, fundamental problems, circuitry and type of testing and so forth. This, what we see on the slide now, which is basically a 4-terminal test, that persisted in the technology from day one all the way up to the present. And for a long time, up until about 1990, that was the only technology available. So all of your testers operated pretty much the same. And then the differences came in. Well, how well were they designed and engineered? How accurate were they? You know, the typical considerations that you would have with any piece of test equipment. On the other hand, around 1990, the Clampon came on the market. And with that, all you're doing is you clamp on your ground rod or your grounding conductor where it's coming down out of the bus bar. And bingo, you have a measurement. So, wow, isn't this great? You're not walking around driving probes in the ground and things of that sort. And so it seemed like a revolution. Well, yeah, in some regards it is, but in some regards there are some caveats associated with it. And the two main ones, easy to keep in mind, the fundamental problems that you have pretty much with all electrical issues, shorts and opens. So, okay, what's an open? Well, the way a Clampon worked was the tester, the Clampon tester, you're holding it in your hand and you clamp the jaws over the top of the ground rod and you've energized it. What it's doing now is it's establishing a high frequency test current inductively from the rod through the soil, and then it finds its own return. So we see in the slide that we have up posted now, where you see C2, that's your current return. So the operator put that where he wants it. With a Clampon, the tester does what it wants to do. it finds its own return, which is typically the grounded utility. And then your test current loops back through the grounded utility and comes back to the jaws of your tester, and it looks at the voltage drop around that loop. And then it posts a resistance on your display. Well, this is very similar now to what we looked at in the dead earth method. It's basically doing the same thing that the dead earth method does, which is find a low resistance return and give you a loop resistance of the whole thing. But the advantage over the dead earth method is, in the dead earth method, the return being something like the water pipe system, that can be putting a lot more resistance into your measurement than you think. And you get a high reading and you don't know where that's coming from. Whereas in the Clampon method, the utility typically can be relied on to have a very low resistance return. And so it's not introducing too much of an error into your measurement. And so your measurement is usually pretty accurate. However, what about if you're trying to commission a new ground and you haven't hooked it up to the utility? That's an open circuit and a clamp-on cannot be used. Bingo, end of story. The other issue is what we call a short in an electrical system, and as it pertains to using a clamp-on, that would be where your test ground has been multiply connected back to your system. So, with a clamp-on, if you're only testing a single rod, well, you're in good shape. But what about if you're testing a grid? Well, in many cases, that grid may be connected at every corner back to your electrical system. Or what about a tower ground with a ring around it? Typically, the guy wires are connected as part of the grounding system. So now what happens is you clamp onto a convenient point and you energize the tester, but now your test current finds a short circuit. It goes over to the other connections to the electrode, to the ring, or to the grid, and it just circulates back to the tester. And you got a beautiful low reading because there's nothing in there but metal. And that's essentially a short circuit. And the reading it gives you is just a continuity test of the grid. It doesn't mean anything. So those are the two main problems with using a clamp-on. So it's a great tester to use where it applies, but you do need to be aware of the limitations. And the third thing is also you can't proof your test result, whereas with a fall of potential, if you're dealing with a client, you can look at your fall of potential and graph it, and your client can look at that and can see that you did it correctly and that your reading is reliable. Whereas with a clamp-on, it does what it wants, and the operator has to have applied it correctly and has to, basically take the assumption that what was shown on the display is accurate. Now, usually a competent operator, and if he's just working for himself, that's usually not too much of a problem. But where third parties are involved, then, that can become difficult. Okay, that's kind of a fundamental look at the clamp-on, which I'm pretty sure a lot of you are interested in. Another thing that I could talk about, however, is also, because I think I still have a couple more minutes, is talk about what is called lazy spike. Now, in the industry, a lot of issues that you run into with doing a typical ground test where you're driving probes into the ground. What about if you're doing lighting grounding on an airport, for instance? You got nothing but tarmac all around you for hundreds and hundreds of feet. How are you going to drive probes? Well, you don't necessarily have to. there's a thing called the lazy spike method. This is with the improvements that we've now had in technology. With an older tester years ago, forget about it. But with modern testers, the sensitivity is very high. And so in many cases, surface contact is enough to put your test current into the ground and enough to sense a voltage drop. So instead of having to drive a probe through the tarmac, for instance, which you're probably not allowed to do, instead you use some even the metal probes themselves will sometimes work, but it's better and more effective to have something that mates more closely with the underlying surface of the ground. So a coiled metal chain would be a good thing to use as a probe. And you throw water on it to increase the conductivity of the current. And then you use two coiled metal chains in place of driven spikes. And yeah, you can actually do an effective ground resistance test by that measurement. And the safeguard here that you have with new testers is new technology. A good tester will tell you if anything is wrong in your test circuit. So if the tester isn't making enough contact, you'll get a message up on your display and it'll tell you that. So you don't waste time or you don't walk away with a bad measurement that doesn't mean anything and you don't know that. So the improvements in the modern testers do make it possible to do surface probes and still do a fault potential test or a slope method or whatever it is that you want to do and still walk away with good data. So just, don't be dismayed by not having a lot of ground around your test area. That does not put you out of business. And then let's see, the last thing I can talk about, because I think I still have 5 more minutes or so, is also what we call art method. This is where you are typically connected back to your utility. And in the old days, in order to get a good ground resistance test of your on-site ground, if your system has been connected, then you're paralleled in with the utility ground because the utility is running a grounded neutral back to the transformer that services your site, and that's grounded. And unless you broke that connection from the ground bus to the neutral bus, then otherwise you run a test, your test is perfectly good. You're going to get a good measurement, nothing wrong with it, except that it's your local ground paralleled into your utility ground. So, okay, you see an ohm and a half. Well, yeah, you do have an ohm and a half protection there. It's not a false reading or anything like that. You do have that degree of protection for your electrical system, except that it's not all being provided by your on-site ground. It's including your utility ground into that, which is generally good. But what about lightning strikes? Well, they're not going to travel. Lightning wants to get into the ground as quick as it can. It's not going to travel 2 miles back to the utility generator if it can get away with it. So it's going to try to go to ground locally. And so you would, to divert that effectively, you would want to have your local ground good enough to provide that degree of protection. So how do you test that then? How do you test your local ground without having to break your utility ground? And you use a tester that has a built-in current clamp. And so this is, in our catalog, we call this the art method. There are other suppliers who use their own terms, but you're going to see this in the literature easily enough. But this is where you get a current clamp that plugs into the ground tester. And all you're doing is you're hooking up to do your test just like you would any other time, and you've got a lead going from your ground tester out to your ground rod, and typically that's hooking onto the head of your ground rod, or maybe it's alligator clipped onto the grounding conductor, a foot or so above your ground rod. And now you're going to take your current clamp and clamp that downstream of your alligator clip. And when you energize your test, what's now going to happen is that the current clamp is going to read how much test current is going to ground through your on-site ground. And it's going to tell the tester, okay, I've got 1.5 milliamps out of a possible 5 milliamps or whatever, within the parameters of your ground tester. And so now the tester is going to make its calculation of resistance based on how much provided current is going to ground through your on-site ground, and it's going to ignore how much goes back through the utility ground. And that's sometimes it's called the ART method. Like I say, it does have other terms associated with it, but fundamentally, that's the way to test your on-site ground if you're connected to the utility and without having to lift the connection to the utility. And with that, I think we have pretty much come to the end of the allotted time. So once again, I thank everyone for your attendance, and you are welcome to contact me with any issue, and I will be glad to help you accordingly.
Thank you so much, Jeff. That was a wonderful presentation. Does anyone have any questions before we lose him?
Thanks, Jeff. Appreciate it.
Thank you so much.
Okay, let's see. Eric, I see you at the moment. And I'm sorry about there were a few issues there. I thought they